Hi everyone! Welcome to part 1 of chapter 3. This chapter is all about compounds and the elements that make them up. Today we are going to talk about the states of matter, so solid, liquid, gas, and learn how to differentiate between them. We're also going to talk about mixtures and how we know whether things are mixed rather than just chemically reacted. We're also going to look at chemical and physical changes and chemical and physical properties. And then we're going to wrap up by talking about the natural state of some elements, which is going to lead us into next time really starting to get into compounds. So lots to cover today. Let's go ahead and get started. So we're going to start off by talking about the states of matter. So matter exists as 3 physical states: solid, liquid, and gas. And if you've ever taken a chemistry class before, or probably any science class, likely you've studied this already, but I'm going to go ahead and go through it to make sure that we're all on the same page. So a solid has definite shape and definite volume, okay? And it's independent of the container. So essentially this means it doesn't matter what you stick your solid in, it's always going to have that same shape and that same volume. So for example, you're probably sitting on a chair. That chair is going to have that shape whether it's in your bedroom or outside in the yard, right? It has a definite shape and it has a definite volume. It's always going to take up that same amount of space, but it doesn't matter where it is. So that's how we know it's a solid. Most solids, like ice over here, are what's called crystalline solids. Okay, they have this regular, repeating, 3-dimensional geometric pattern. So ice is actually really cool. Ice makes little hexagons. So you can see these repeating hexagons over and over and over again in the ice. And that has to do a lot with how water is shaped. And we'll get into that more later, but I'm going to talk about it a lot in this class. Ice is really, really cool. But anyway, most solids have crystalline shapes. They're crystalline. But some solids are what's called amorphous solids. So our examples here, and I want you to remember these examples: plastic, glass, and gel. Okay, those are the 3 that I want you to remember as amorphous solids. These are not crystalline. Okay, they don't have a regular geometric pattern. So if you look down here, these atoms or these molecules are all just kind of shoved together any which way, and they don't have any kind of pattern to them. So that's why they're called amorphous. That means without shape. So they're just kind of mushed together. An example, I realized I didn't give you one, for our crystalline solid, other than ice, would be salt. Okay, likely when you've, maybe put some salt on your food, you've noticed that those little salt crystals are all about the same size, right? And they have, if you looked at them at a very, very small level, they would have a regular repeating pattern. And they just kind of be organized like this. Okay, so those are crystalline solids. And like I said, most solids are crystalline solids. Very few are amorphous solids, but plastic, glass, and gel are going to be our examples. All right, moving on to liquids. So liquids have a definite volume, but not a definite shape. So what I mean by that is if we had, say, a bottle of water and we poured it into a graduated cylinder, we could measure the volume of that water, right? If we poured it into a beaker, we could measure the volume of water in the beaker, or in an Erlenmeyer flask, right? We could keep pouring the water into these different things. They all have different shapes, so the water takes the shape of that container, which is why we say it does not have a definite shape, but it would have the same volume in all of those containers. So it has a definite volume, right? We can measure the volume pretty easily, but it doesn't have a definite shape. It'll take the shape of whatever container you put it in. These liquid particles are held together by strong attractive forces. Okay, the strongest attractive forces are actually a solid. Solids have really, really, really strong attractive forces that kind of lock all of those atoms and molecules in place, which is why they're a solid. They're stuck together really, really, really well, and so they make a solid. Liquids are stuck together fairly well, but not as well as solids. They're weaker attractive forces than solids, but still really strong. So they're able to keep them kind of together, but not locked into place, which is why these liquids have a definite volume, right? They all stay together, they flow, but they don't have a definite shape because they can easily slide past each other. Okay, so liquids are what we call fluid. They're able to take the shape of whatever container they're in. But like I said, those attractive forces are strong enough that the particles don't like fly away as a gas, right? They keep them together, but not strong enough to lock them in place. And then gases have an indefinite volume and no fixed shape. Gas particles are mostly just kind of empty space. Like if you think about the gas in your room, right? There's gas filling all of your room. That's why you can sit there and breathe, right? You're breathing in the oxygen that's in the air. There's also nitrogen and carbon dioxide and lots of other gases that are present. But the gas particles themselves are really, 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 really small. Most of a gas is just empty space. Okay, it's because these gas particles are separated by very, very large distances compared to the particles themselves. So the cool thing is that gases can be compressed. Okay, so an example of a gas that's compressed would be maybe you like to go paintballing, right? And you have to get one of those CO2 cylinders to put on your paintball gun. That has carbon dioxide that's been compressed to a very, very, very high pressure, right? There's a lot of carbon dioxide molecules that are in that CO2 cylinder, which is why you can shoot off that paintball with such speed. Same kind of thing if you go to, Target and you buy a helium tank, right? That's compressed helium. There's a ton of helium molecules, right, or helium atoms in that tank, and they've been squished close together, so it's under really high pressure. So that's what we mean by when we say compressed. We're squishing the atoms or the molecules together under really, really, really high pressure. But they can also be expanded, right? So like if you let off some perfume, right? If somebody sprayed a perfume in the corner of the classroom, that perfume molecules would actually expand and start to fill the classroom, which is why you can smell that perfume even though you're not sitting right next to the person who sprayed it. Maybe you're sitting a couple people away, right? So gases can be compressed and expanded almost indefinitely. So essentially what that means is we can kind of keep squishing gas molecules together, and you can keep going and keep going and keep going because the gas particles themselves are so small that you can cram a lot of them in there. But the same thing, you can expand them almost indefinitely as well. Gases will always fill whatever container you put them in. So gases have an indefinite volume, so we can't measure the volume of a gas because we can just keep expanding it or compressing it. So it doesn't really have a volume. And it has no fixed shape because it'll just take the shape of whatever container you put it in, whether that's a CO2 cylinder or a helium tank or the classroom. Doesn't matter. So 3 states of matter: solid, liquid, and gases. So as you can see here, this is a crystalline solid, right? Those particles are packed really close together and in a regular repeating pattern. And again, the thing that makes it a solid is that they have really strong attractive forces happening between those atoms, which are keeping them kind of locked in place. The liquid, you see, our liquid particles are not organized like a solid. They're not locked in place. They can kind of move past each other and flow around. They have strong attractive forces that are keeping them in the liquid, but not strong enough to lock them into place like a solid. And then the gas particles, you can see the gas filled this entire container. It's not sitting at the bottom anymore like the solid and the liquid. It's now gone and filled its container. It's expanded to fill the container that it's in. And the gas particles are not attracted to each other. They just kind of zoom around doing their own thing, and they fill whatever container you put them in. And you can convert from a solid to a liquid to a gas without changing the identity of the substance. And what I mean by that is, like, say we had some liquid water, right? You got a bottle of water. You could freeze that bottle of water and it would still be water. It just now happens to be a solid, right? But it's still water. You can thaw it and then drink it. It didn't change in any way, right? It was just a different state of matter. It's the same thing if you took that water and you dumped it in a pot on the stove and you cranked it up and started to boil it, right? That would turn it into gaseous water or steam. But we didn't change anything about the water itself. It's still H2O. all we did was take it from a liquid to a gas. So we can go through these different states of matter without changing the identity of our substance. And like I said, these attractive forces are what determine whether something is going to be a solid, a liquid, or a gas. And we're going to talk more about these attractive forces in a later chapter. I just wanted to introduce them now to get you kind of started thinking about them. But like I said, attractive forces are the strongest in solids, which is what makes them have that definite shape. They're weaker in liquids, but they're still strong enough to keep them kind of all together, right? And then they're really weak in the gases, which is why those gas particles all just float about, right? They move away from each other and fill whatever container they're in. And then down at the bottom, those are just some examples of solid, liquids, and gases. Alrighty, moving on to classifying matter. So remember, matter was anything that has mass and occupies space. So most things are matter. So we need to have some categories to separate these bits of matter into. So one of these is a pure substance. Okay, a pure substance has a definite fixed composition. It can be either an element or a compound. Okay, so here in the picture, we have two different pure substances. This up here is sugar. Sugar is a pure substance, right? If you go and you buy a bag of sugar from, I don't know, Save Mart, right? That whole bag is just sugar, C6H12O6. But all of it is sugar. There's not randomly like some salt in there. It's all sugar. And then this, we're going to assume this is deionized water. So it's taken out all of the ions. This is just pure water. So this down here is pure H2O, and this is C6H12O6. So both of these are compounds, right? But they are both pure substances because this one up top is just sugar and the one on the bottom is just water. So they are pure. A mixture is exactly what it sounds like. It's when we mix together two or more pure substances. Okay, and these mixtures can be either homogeneous or heterogeneous. So we're going to look at what those are. So a homogeneous mixture means that it's uniform throughout. So you remember that sugar on the previous slide. All I did now was I dumped my sugar in the water and stirred it around. And I made sugar water, right? No surprise there. If you dump some sugar in some water, you get sugar water. But the way that we know it's a mixture, right, is that it looks, we've mixed together two pure substances, and what makes it homogeneous here is that it looks the same throughout, right? When I look at it, it really just looks like water, right? It's clear. Some of it doesn't look different from any other bit. It doesn't matter if you take some of the sugar water from the top or some of the sugar water from the bottom, it's all going to be the same because it's mixed throughout. So this is homogeneous mixture. A heterogeneous mixture will have a different composition depending on where the sample is taken. So a common example I give for this is sand. Okay, sand, if you look at sand, right, some of the little pieces, the little flecks are kind of golden, where some are darker and maybe some are glittery, right? But if you take a different sample of sand, take a different scoop, you're not always going to have the exact same pieces in each scoop, right? The composition of your sand could be different depending on where you take it. Kind of a different example would be maybe like a salad. A salad is a heterogeneous mixture. So if you take a scoop of some kind of salad, right, maybe it's a Caesar salad, right, you're not going to have exactly the same number of croutons and lettuce and dressing and Parmesan or whatever's in there, right? It's going to be different in each bite. They'll be similar, but they won't be exactly the same. Another way it can clue you into these heterogeneous mixtures is you often can see the pieces of the heterogeneous mixtures. Like you can tell it doesn't look uniform throughout. So, my example, though, that I usually give that you probably should remember would be sand. All right, so we can actually go through and separate mixtures, right? We actually already did this lab. We had a mixture of 4 different substances, and we were able to separate all of those 4 different substances, which is pretty cool. So the components of the mixture don't lose their identities. That's how we know it's a mixture and not a reaction. right? So when we mix two things together in lab, right, sometimes they'll just mix, like sugar and water make sugar water, but sometimes they will react and make something new. Okay, but if it's a mixture, then we can separate those pieces back out. One of the ways that we did this in the lab was evaporation, right? We were able to take our salt water and we evaporated off the water and we were left with salt. And we did the same thing with the sand in the water, right? We were able to evaporate off all of that salt. We will commonly in this class filter substances to separate liquids and solids, but you can also, sometimes things will float and other things won't. And the example down below is magnetism, which is cool. So on the left-hand side, right, we have sulfur. Sulfur is this yellow powder. It's really smelly, but that's what it is right there. So sulfur, you can see, is not magnetic. It's not at all attracted to the magnet, but iron is magnetic. So if you hover a magnet over iron, it jumps to it. So if you mix together these two substances, you got a bowl and you stirred them all up, you could separate them back out by using a magnet to pull out all of the iron, and then the sulfur would be left in there. Pretty cool, right? I think that's not a way that we normally think of separating a mixture, but it's a really cool example of using some of these physical properties to separate our mixtures. All right, so looking at this, before we get to the practice problem, so pretty much everything, like I said, is matter. If it has mass and occupies space, it's matter. Our matter can be separated into two different categories. The first one is pure substances, and pure substances can either be an element or a compound. So an element is just aluminum or iron or something like that, whereas a compound is something like H2O, where it's elements that have been bonded together. Okay. But if we didn't have a pure substance, if instead we had a mixture, then we have two different types of mixtures. We can have homogeneous mixtures or heterogeneous mixtures. So remember, homogeneous mixtures will look the same throughout. Our example there was sugar water. And heterogeneous mixtures, like I said, my example is usually sand. So our example down here says, which of the following is a heterogeneous mixture? So I want you to pause, think about it, come back when you're ready to see the answer. All right, so our answer here is soil. Soil is our heterogeneous mixture. In soil, there's lots of different things. There's seeds, maybe some weeds, right? There's a lot of things happening in the soil in addition to just the dirt. And a lot of times you can see those individual pieces. Remember, like I said before, if you can see the individual pieces, that usually clues you in to the fact that it's a heterogeneous mixture. All of the rest of these, so like baking soda, that's a pure substance. And so that would be a compound. Gasoline is a mixture, but it's homogeneous. Okay, it's a mixture of a bunch of stuff, but it looks the same throughout, right? We don't have different pockets of gasoline that have different stuff. It's all just the same. Grape juice is also a mixture, and this will also be homogeneous. Because again, it looks the same throughout, right? It's got sugar, it's got water, it's got other things in there. And then copper metal is going to also be a pure substance, and this is an element because this is just copper. Okay? Alrighty, let's try another one. Which of these is a homogeneous mixture? Go ahead, pause here, come back when you're ready to see the answers. All right, our answer here is maple syrup. Again, kind of like one of the examples before, this one's got water, sugar, and mostly that's it actually, in maple syrup. So that one is our homogeneous mixture because again, it's a mixture, but it looks the same throughout. Our Italian salad dressing would be a heterogeneous mixture because you can see those individual pieces. Carbon dioxide would be a compound, and mercury is an element. All right. Let's try another one. Filtration is a common method to separate components of what type of mixture? So go ahead, pause here, think about it, come back when you're ready to see the answer. So we filter things that are a heterogeneous mixture, and it has to be specifically a solid in a liquid, okay? I want you to think of this filtration. Whenever you think of filtration, I want you to think of making coffee. And not like in your Keurig, but old school coffee, like where they used to have filter paper and coffee grounds, right? And so we would use this filter paper, right? And the filter paper would catch all the little coffee grounds, and then the water would come through, and that would be what we drink, right? But that's how we would separate a mixture. This is filtration. So all of the solid gets trapped up in a piece of filter paper, and then the liquid comes through. So we separate the solid from the liquid. Alrighty, I want you to go ahead and pause here and work on problems number 1 through 6 on the Chapter 3 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so now we're going to talk about properties of substance. So each substance, no matter what it is, solid, liquid, gas, has a set of properties that are characteristic and give it its unique identity, okay? So let's say, take a penny for example. If you look at the penny, it's a solid, it's coppery, right? It's, got a certain mass and certain density. It has a certain melting point, right? All of these are properties of that penny. These properties can either be physical properties or chemical properties. And we're going to look at what types of properties are physical versus chemical. So physical properties, here's that penny I was talking about, are characteristics that can be observed or measured, and what's important is without changing the identity of the substance. Okay, so it's usually things where if you look at something, you can start to describe it. Like, let's take table salt. It's white, it's a solid, it has a high melting point, right? It has a specific taste. All of those are physical properties because we can taste it. We can test it without changing its identity. These are properties that we can observe without doing anything to it. Once we're done with our test, the penny is still the penny. So some examples here are shape, physical states, that's your state of matter, boilings and freezing points, density, the color, right? All of those things. And there are more types of physical properties. Those are just some examples. But like I said, our example here would be this penny. It's round. It's kind of orangey, reddish, coppery colored. It's shiny, right? All of those would be physical properties because we can describe those properties without changing the identity of the substance. Chemical properties, though, are only discovered by changing our substance. Okay, so the way that we figure this out is we cause it to interact with a new substance. So, for example, sugar. Sugar caramelizes, right? And it smells really lovely. Well, the only way we know that happens is by changing the sugar, right? When we heat it up to a specific heat, it doesn't melt, it actually caramelizes, which is different. That's a chemical reaction. But the only way we know that happens is because we turn it into caramel. And it's not sugar anymore, now it's caramel. So we had to change our substance in order to find that out. Okay, so we only find out these chemical properties by changing our substance in some way, and usually that doesn't let us get that substance back. So like I said, cooking our sugar here, this looks like some flan, caramelizes the top, and that changes the substance. Okay, so those are chemical properties and physical properties. So I want you to kind of, pause there in your mind. Now we're going to talk about physical changes and chemical changes. These are different than physical properties and chemical properties, okay? So physical properties and chemical properties describe something about a substance. So, describe something about sugar, or they describe something about water or about the penny, right? These changes, though, are going to tell us whether or not a reaction happens when we do something to our substance. Okay, so, we have our substance, we do something to it, and we're trying to figure out, is that a physical change or a chemical change? A physical change would mean no reaction occurs. A chemical change means a reaction occurs. Okay, so that's why it's important to figure out physical changes and chemical changes. So physical changes are changes in physical properties. Okay, and usually our change in physical property usually is going to be size and density. That's most often this physical change that we're seeing. Or another common one is the change in the state of matter. But the important thing here is that physical changes do not change the composition. So they do not change the identity of our substance. So an example here of a physical change would be boiling water, right? We're doing something to our water, right? We're boiling it, but we're just changing the state of matter. We're changing it from a liquid to a gas, okay? But it's still H2O. So we didn't change the chemical substance, right? It stayed H2O before and after we did stuff to it. So that's going to be a physical change. Another example here, like this guy sawing wood, okay? When he saws this big old log, he breaks it into two pieces essentially, but each one is still wood, right? It's still the same log, it just happens to be smaller. Okay, so he didn't change the identity of the wood, all he did was change the shape. Kind of like if I tore up a piece of paper, right? I changed the shape of the paper, but I didn't change the fact that it was still a piece of paper. Okay, another example is putting salt in water, right? I changed the shape, right? I've dissolved that salt, but I could evaporate that water back off and get my salt back because it just made salt water, right? So all of these are physical changes because they didn't change the identity of the substance. They just changed the shape or the state of matter, right? But I want you to write down this one. This is one that people get wrong. Phase changes are physical changes. So if something goes from a solid to a liquid, like ice melting, that's a physical change because all we did was change the state of matter. It's still H2O, it just happens to be a liquid instead of a solid, or vice versa. Okay? So since no new substances are formed during a physical change, phase changes are physical changes. Okay? Here's our other example. This is kind of a real-life example of the whole saltwater evaporation. This is actually how we get salt, which is kind of cool. So like your table salt, what they do is they take salt water and they'll kind of spread it out. They wait for the water to evaporate and the salt will be left over. So it's essentially what we did in the lab when we evaporated off all the water and had the salt left, but a lot slower. Okay, so this is a physical change because all they're doing is separating salt water into salt and water. They're not making anything new. It's just they're just separating a mixture essentially. So that's a physical change. Chemical changes, though, I want you to know these are reactions. Okay, this is what we will do mostly in this class. We're going to be doing chemical changes because this is chemistry and it's fun, right? So chemical changes take place when the original substance is converted into a new substance. And this new substance is going to have completely different physical properties, completely different chemical properties. Okay, so whatever is created after this reaction is going to be totally different than what we're starting with. Okay, that's how we know a reaction has occurred. So for example, here is some copper wire, okay? If you take your copper wire and you heat it really, really hot, like in a Bunsen burner, right? You just stick it in the fire. That copper reacts with oxygen in the air and it actually will turn black, okay? And that is because the copper reacts with the oxygen to form copper 2 oxide. So it goes from copper and then it reacts with oxygen in the air to make copper oxide. So our copper changed into copper oxide. Okay, so it's a totally different substance. Okay, it underwent a reaction. And the way that we know that this happened is the fact that it turned black. We are going to have some things to look out for that are going to tell us whether a chemical change is happening or if you don't see any of those things, it's a physical change. Okay, but chemical changes are reactions, and that's really important. So I want you to memorize these characteristics of a chemical change. Okay, so this is a good place to pause, take a screenshot, whatever you need to do, write these down. But you need to memorize these characteristics of a chemical change because these are going to let you know whether a chemical change is happening or not when we do these labs. Okay, and so by observing your reaction, you can tell me, oh, I see it's bubbling. That means it's producing gas. Therefore, I know it's reacting. Or it turned colors. That's how I know a reaction's happening. So you need to know these characteristics of a chemical change so you know that a chemical change is happening rather than a physical change. Okay, so our first one is a change in color. If your substance changes color, then it's undergoing a chemical change. Okay, your example that you can think of for this is, let's take a piece of paper. If I have a piece of paper and I burn it, okay, I stuck it in my Bunsen burner and I burned it, it would turn black, right? It would turn into black ash. That change in color is telling us that a chemical change has occurred, right? Or like this log, right? This log will go from kind of a wood color to black when it turns into ash. Okay, that is a chemical change, that change in color. And I want you to be careful here though. This would be an unexpected change in color. If I mix together, let's say I have a blue substance and a yellow substance and I pour them together and it turns green, well, that's not a reaction. That's just because blue plus yellow makes green. That's just colors, right? When we mix colors together, that naturally happens. So that's not a reaction that's happening. That's just because it was blue and yellow and made green. But let's say you had, a glass of water and all of a sudden that glass of water, without doing anything to it, turned purple, right? That would be some chemical reaction that happened because that wouldn't be something you predict. So when I say this, I mean an unexpected change in color. Okay, another one is a change in smell. My example that I like for this is baking cookies, right? You know when your cookies are almost done because that wonderful smell starts to fill your kitchen, right? That is because cooking is a chemical change. You're changing the batter into cookies, okay? And so the way that we know that is it does actually change color, right? It browns and it looks ever so delicious, but it also, you smell that delightful smell, okay? So a change in odor is also a characteristic of a chemical change. Another one is light production. Really obvious one here is fire, right? Fire is a chemical change. Okay, if you light something on fire, it's going to change its composition. Like again, this log, if we burn this log, we're changing it from wood into ashes. Okay, we've changed its chemical composition. That's a chemical reaction. Another one is gas production. And usually the way that you know gas is being produced is you'll see bubbles. Okay, you'll see bubbles in your reaction, which is really fun. But I want to be clear. When I say you see bubbles, it'd be like if you pour together two liquids kind of at room temperature, just like sitting on the lab bench, you pour together those two liquids and bubbles start to happen. Okay, that would be the gas production that I'm talking about. I want you to be really careful here. The gas production is one that people mess up sometimes. I want you to make a note, not boiling, okay? Because when we boil water, right? Let's say you have a pot of water and you stick it on the stove, then you'll see bubbles, right? But that is not a chemical change. We are seeing bubbles because the gas is turning from liquid water into gaseous water. And like we just talked about before, that's a phase change, right? It's changing its state of matter. It's going from a liquid to a gas. And phase changes are physical changes because even though it's turning into a gas, it's still H2O. It's still water. So not boiling. This gas production that we're looking for is when you pour together two liquids like at room temperature, just sitting on your bench. And if bubbles happen, that means some kind of gas is being produced. Our next one is when heat is released. So again, let's think about our fire. You guys know if you sit around a campfire, that's how you get warm, right? Because that fire is producing heat. Well, that fire producing heat, that's telling you a chemical reaction is happening. A chemical change is occurring. Okay, and we call this release of heat, we call it exothermic, because heat is exiting our reaction. So if our reaction feels hot, right, like if you pour together two liquids and it starts to get warm, which is really cool, right? If you pour together two liquids just sitting on the counter and your beaker starts to get warm, that's always like, whoa, that's so cool, right? And that means that heat is being produced by your reaction, and it can heat up your hands, which is neat. But the reason we call it exothermic is because heat is exiting the reaction. Okay, so exothermic, heat is exiting, it's being released. We can also have, and so these, when heat is being released, your reaction will feel hot. Okay, you can have the opposite also happen too. Like if you pour together two liquids on your bench and you touch your beaker, sometimes it will feel like ice cold. And you're like, wow, none of this stuff was cold to start with. When I poured together the liquids, it starts to feel cold. And that's because heat is being absorbed. So this is when it feels cold. Okay, and heat is being absorbed. It's taking in heat. So we call this endothermic. So again, exothermic, heat is exiting. Endothermic means heat is coming in. It's being absorbed. Okay, and exothermic will feel hot and endothermic will feel cold. So if there's any kind of temperature change happening with your reaction, then that means it is in fact a reaction, and you just need to figure out, is it exothermic or endothermic? And our last one, and this one is a little bit tricky, this one is called formation of a precipitate. Okay, it's so again, you're gonna have two liquids just sitting on your bench, and when you pour them together, it gets cloudy. Okay, maybe it turns white or it turns yellow, but something, when you pour together those two clear liquids, it's not clear anymore. Okay, and that cloudiness is a solid that's forming. If you let it sit long enough, that solid will actually drop down to the bottom, which is really cool. So if you pour together two liquids and stuff happens, whether it gets cloudy, it looks like a solid, whatever it is, if you pour together two liquids and stuff happens, that means eventually it will form this precipitate, so it is a chemical reaction that's happening. So again, I want you to memorize all of these characteristics of a chemical change so that when you see something happen in lab, you can tell me, yes, a chemical reaction is happening, and here's why, this is what I'm observing, or no, a chemical reaction is not happening because I don't see any of these things happening. Okay? So here's an example. Okay, remember before I told you the physical properties of a substance change after a reaction happens, right? After a chemical change occurs, we end up with a new substance with totally new properties. So here's our example. So this stuff on the left-hand side, this is sodium metal. Okay, it's kind of pretty, actually. It's a really soft metal. So normally when we think of metal, we think of things that are really, really hard and solid, right? Maybe like a piece of, iron or an aluminum can, right? And things that are really solid. Well, sodium metal, you can actually cut with just a regular old butter knife, like from your kitchen. You can just cut this into little tiny pieces. So it's not something that you would normally think of being a metal. It's pretty soft. The cool thing about sodium metal is that it's an alkali metal, which means that when you put sodium metal into water, it explodes, which is cool. It's a really big explosion too, depending on the size of the metal that you have. So sodium metal, super soft metal, cut it with a knife, explodes in water, really cool. Chlorine gas though, so chlorine gas, this is actually what it looks like. It's kind of like a greenish yellow color, and it's really poisonous. So even breathing in a little bit can be really dangerous or potentially fatal. Okay, so the cool thing is you mix together, an explosive metal plus a poisonous gas, and you get stuff we put on food. Sodium chloride. This is table salt, NaCl. Okay, so the thing I'm trying to make a point here is that sodium chloride, this table salt, right, the stuff we put on our food every day to make it taste good, is really made from explosive metal and poisonous gas. So the properties after this reaction happens, after we mix sodium and chlorine together, the properties of the substance completely change, right? We're not worried that our table salt is going to blow up if we put it in our boiling water to make pasta. We're not worried that it's going to, turn into a green gas and kill us while we eat our dinner, right? This sodium chloride, this table salt, has completely different properties than the two things that came together to make it. So the properties of a substance after a reaction are totally different. And again, if we think about our characteristics of a chemical change, you can see here a color change occurred, right? That chlorine gas was green, or the metal was silvery, right? And then it turned white. So that's one of our characteristics of a chemical change that we can see there. Okay, so again, the physical properties of a substance and the chemical properties of a substance, totally different after a chemical change. All right, so here's some common physical and chemical changes. So like the first one here, I'm not going to go through all of these. You can read them, but like iron rusting. So let's say you have some old car in your backyard. It likely is rusted, right? That metal probably started off nice and silvery, but over time, it reacted with the oxygen in the air and turned to reddish brown rust. Okay, so that's a color change that we're seeing there. It went from nice and silver and shiny to reddish brown and kind of ugly, right? So it's a color change. That's one of our characteristics of a chemical change. An example of a physical change is boiling water. Remember, that's one that people get wrong a lot of times because they think boiling water has bubbles. That's gas production. No. It's, yes, a gas is forming, but it's because we put in heat to change the state of matter. Remember, when we think about gas production, that'd be like two liquids poured together at your bench, no heat being added. Okay, so boiling water is a physical change because that water is just changing from a liquid to a gas. Let's think of another one. Let's do digesting food. That's a fun one. Digesting food is a chemical change. So in your stomach, you actually have hydrochloric acid. So that stomach acid you guys have heard of, that is HCl. And we'll learn about hydrochloric acid in this class. But the hydrochloric acid reacts with your food to digest it, right? It actually goes in and starts to break it down and kind of eat it away. So one of the ways that we know that this is a chemical change that's happening is sometimes it produces gas, right? It can give you kind of like heartburn and things like that. So that is how we know it's a chemical change. Okay, so remember, we've learned about physical and chemical properties and physical and chemical changes. Those are different, okay? So I put them all on this table, okay? So up here, right, up here we have physical properties, and those are things we can observe about our substance without changing it at all. So color, shape, right, and this is just by just looking at something, like a soda can. We know it's a solid, it's got kind of a circular shape, it has a specific density, all of that kind of stuff. Whereas a chemical property, the only way we can figure out the chemical properties of that substance are to change it in some way. Like we can burn up a piece of paper and then we know it can burn, but it's not paper anymore, right? We had to change it to find that out. Or that iron can rust. Well, when that happens, it's not iron anymore. Now it's iron 3 oxide, which we call rust. So all of these chemical properties, we only find out by changing our substance into something else. All right, and then physical changes, right? So this is when a change actually happens. This up here is, no change, those properties, and down at the bottom is when a change happens. And we'll need to know, is it a physical change? That means no reaction happened, right? Physical changes, no reaction. Your identity of the substance changes. Your identity of the substance doesn't change, but it may change shape. It may change state of matter, right? But it's still like H2O would still be H2O. A chemical change, though, this is our reactions that are happening. Okay? We're converting something into something else. And that's where we need to know those 7 characteristics of a chemical change. So I would recommend have this handy somewhere so you know the difference between physical and chemical properties and physical and chemical changes. All right, let's go ahead and practice this. So which of the following is a physical change? Go ahead, pause here, come back when you're ready to see the answer. All right, so our answer is grinding rock into a powder. So if we take that rock and we just kind of crush it, right, it's still got the same identity. It's still that same rock. Just now, instead of being one big rock, it's a lot of little tiny rocks, right? But it's still made up of the same stuff. We didn't change it in any way. So that's a physical change. So this one we would describe as changing shape. Whoop. Anytime we change shape and we don't do anything else, that's just a physical change, like tearing up a piece of paper, right? It's still a piece of paper, just in smaller pieces. All of the rest of these are chemical changes. So hydrogen and oxygen reacting to form water, our key there is that they reacted, right? A shovel rusting, that would change its color. An acid and a base reacting to form water. So again, we see that term reacting. And then burning sugar, that is also a chemical change because you would smell it and also we would see a change in color. So all of the rest of these are chemical changes, just that top one is a physical change. All right, here's another one. Go ahead and figure out which one of these is a chemical change. Pause here and come back when you're ready to see the answer. Alrighty, so our answer here is lighting a match. So what I want you to think about, anytime we're thinking about chemical changes, I want you to think of those 7 characteristics of a chemical change and ask yourself, are any of those happening? Melting aspirin, this first one, your key here is melting, okay? Whenever we melt something, that means we're just changing the state of matter. That's a phase change, which is a physical change, okay? Think of it like melting ice, right? Changing it from a solid to a liquid, but we're not changing the fact that it's H2O. Breaking a plate is changing the shape, right? But all we did was break that plate into a bunch of pieces. It'd be a bummer, but it's still a plate. We didn't change anything to it. Boiling antifreeze, again, our key here was boiling, okay? Again, that's going to be a phase change, which is a physical change. We're going to change it from a liquid to a gas, but we're not changing its identity. And then putting sugar in tea, again, that's another physical change because all we did was make our tea sweeter, right? Now we have sugary tea. It's not a reaction in any way. We're just dissolving some sugar in our tea. Dissolving is not a chemical change. Like if we take some salt and dissolve it in water, we make salt water, right? We didn't change the identity of our stuff. We just kind of mixed it together. So that's a physical change. Alrighty, so I want you to go ahead and practice this. Do problems number 7 through 9 on the Chapter 3 lecture worksheet. We've got a little bit left to cover for today. So once you're done, come back and we'll keep going. Alrighty, so we're going to spend some time moving forward talking about pure substances. Up until now, most of this chapter has kind of been talking about mixtures, right? We separated our mixtures and we looked at how to do that. But now we are going to focus on pure substances. Today, we are going to talk about elements, okay? And then next time and the time after that, we are going to talk about compounds. But for today, we're just going to talk about our elements, okay? So our elements in general tend to be really reactive, and they combine with other elements out in nature to form compounds. It's super rare actually to find any elements that are out in nature in their pure forms. I mean, they do happen, right? Like the oxygen in the air. We also have nitrogen in the air. So those are some examples. And there's also like gold and silver and platinum that we can find kind of uncombined in nature. But most elements, because they are so reactive, we don't see them as pure elements out in nature. We actually find them as compounds. And then if we need to use a pure element, we actually go through and separate that compound into its pure elements, which is kind of cool. But like I said, most elements out in nature are not just floating around as pure elements. They're floating around as compounds. So our air, though, does have some pure elements in it. It's composed mainly of nitrogen and oxygen. Our air is mostly nitrogen, okay? But it does have, enough oxygen in it for us to be able to breathe, which is great. Really appreciate that. And it's a homogeneous mixture. Okay, these pieces, right, this nitrogen and oxygen, carbon dioxide, a bunch of other things that are floating around in our air is mixed completely, and it's the same throughout, right? So we don't see the individual particles in the air, unless you have like really bad air quality, but in general, right, we don't see individual pieces in our air, and we know it's a homogeneous mixture because we breathe the same no matter where we are in our house, right? You don't randomly breathe better in your kitchen than you do in the living room, okay? So it's a homogeneous mixture. Everything is mixed the same throughout. And these two elements, nitrogen and oxygen, are what we call diatomic elements, which means rather than just being nitrogen or just oxygen, they actually exist as N2 and O2. You've likely heard that oxygen is O2. Kind of a fad that there was, more like a couple years ago, where these like O2 bars, especially down like in LA, you could go to an O2 bar and you could breathe in some oxygen. Doesn't that sound kind of silly? Anyways, but they had places where you could go and just breathe kind of concentrated oxygen. They said it helped to relax you and all of these things. I think it's kind of bogus, but you believe what you believe. But the thing that I'm trying to make a point of here is that oxygen is O2 and nitrogen is N2. Okay, so these molecules that you see floating around, right, they have two elements bonded together. That's how nitrogen and oxygen exist when they're floating around. Not single elements, but diatomic elements. Okay, there are actually 7 elements that exist as diatomic molecules out in nature. Okay, and I want you to remember all of these. So our elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And so here's their symbols. So, like I said, they all exist as diatomic molecules. So whenever you find them out in nature, they are all going to have a 2 after them. Like hydrogen is H2, nitrogen is N2, oxygen is O2, right? And that's how they exist in nature. Okay. So I want you to remember these 7 elements. The way I want you to remember it is Hofbrinkel. Okay, I know it sounds a little bit silly, but otherwise memorizing these 7 elements is a little bit cumbersome. If you just remember, diatomic elements, I remember Hofbrinkel, then you'll always remember them. So it's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. See, I'll say it again. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. So if you remember Hofbrinkel, then you remember all of the 7 diatomic elements. So again, the cool thing about diatomic elements is they all exist bonded, right? There are 2 of those atoms bonded together out in nature. Alrighty, that is actually where we are going to stop for today, because next time we have a lot to cover about compounds. We covered a lot of ground today. We talked about the different states of matter. We talked about physical and chemical properties, physical and chemical changes. We also looked at, mixtures and homogeneous versus heterogeneous versus pure substances. And then we talked about our 7 diatomic elements. So covered a lot of ground today. Make sure you get some practice on it, because in the next lecture, we're going to start talking about compounds. And this is the first chapter that I think it starts to get a little bit tricky in this class. So make sure you feel really, really solid about everything we've done up to this point. Okay, and you also, so do problems number, we started with number 1 all the way through number 10 on this chapter 3 lecture worksheet before you go on to the next lecture, because like I said, the next lecture we are starting bonding and nomenclature. And it starts to get a little bit trickier. So you want to make sure you have a good foundation before moving on. So as always, if you have any questions, make sure to send them my way. I am more than happy to help you, straighten out any of these concepts that get a little confusing. But if you don't need any help, then keep working hard, and I will talk to you guys next time.